Hi everyone, I'm creating this video for my AP Physics C summer assignment, and my topic is the conservation of angular momentum. So let's get started. The definition of angular momentum is momentum will be conserved as long as there is no external torque. So if we do a quick review, torque is a measure of how much a force acting on an object causes that object to rotate. And the equation for torque is RF sine theta, which goes to RF because when an object is rotating in a circle, I'm horrible at drawing. So as long as the object is rotating in a circle about an axis, so let's say there's a rod here and it extends out a little bit further than the actual circle is. So if it's rotating and something is pushing on it, say a hand is pushing it, that's a hand, and it's pushing it this way, the angle it creates here is theta, which is 90 degrees, and the sine of 90 is 1. So that gives us the equation RF. So now that we've done a little background, let's go ahead and take a look at the equations for angular momentum. So angular momentum for an extended object, such as a sphere that's rotating on a circle on an axis, is L equals I omega. Now if we take a closer look at that, we can find the units. So L equals I omega. So L equals, and the units for I, which is inertia, is kilograms per meter. And the units for omega, which is angular velocity, it is meters. So let's make that meters squared per second. So here we have kilograms per meter squared per second. And in Ms. Sanders' class, we often refer to that as a kilogrooter. So if we continue on, we have L equals I omega, which I goes to mr squared because that is the most commonly used inertia equation for a floating object. And omega is V over R. So we can cancel out our R's, or one of our R's, which gives us the equation mVr. Now mv is the equation for momentum. So that gives us the equation L equals P, momentum, times the radius of the object, which happens to be the angular momentum for a point object. Then we have our equation right there. So let's begin with our equations. We have L equals I omega and L equals R times. So what is I? I is inertia. And so here I wrote out the common moments of inertia for the most commonly used shapes. And if you want to go ahead and pause the video to take a second to write all of these down, I know in Ms. Sanders' class she recommended that we memorize them for reference. Okay, so now let's do an example. So we're going to start out by drawing a picture. And this is a horribly drawn turntable that is very lopsided. And so now we're gonna draw, does that even look like a circle? The record. So this is our record turntable system. So as of right now, the turntable, the record, is not on the turntable, but it's going to drop onto the turntable instantaneously, creating a perfectly inelastic collision. So let's start out here. We know the radius of the turntable and the disc, and that is, we're going to call it R. And the mass of the record is going to be 1/5 of that of the turntable. Okay, so we're going to use the equation L equals IR. So let's find our I's for both the record and the turntable. So the I for the record is going to be 1/2 mR squared, and the I for the turntable is also going to be 1/2 mR squared, because they are cylinders. So let's say momentum is conserved. So L initial equals L final. So that means when the record drops onto the turntable, because the I increases, the omega is going to decrease. So let's see if that's true. So let's write our equation. So first we have just the turntable. So I of the turntable times omega naught is going to equal I of the turntable and omega final plus I of the record times omega final. So let's expand that. Let's write it out for each of the I's. So we're going to have 1/2 mass of the turntable times radius squared omega naught equals 1/2 mass of the turntable radius squared omega final plus 1/2. But because the mass of the record is 1/5 mass of the turntable, we're going to write 1/5 mass of the turntable times radius squared omega final. So there's our equation. So it's pretty long, so let's see if we can take anything out of it. So I see that every part has a 1/2, so we can take out a 1/2. We can also take out mass of the turntable and radius squared. That leaves us with omega naught equals omega final plus 1/5 omega final. So if we add those up, we get omega naught equals 6/5 omega final. Now we want omega final by itself, because that's what we're looking for. So let's transfer that over. We multiply by 5 and then divide by 6. So then that's going to give us 5/6 omega naught equals omega final. Which means that the angular velocity of the record and the turntable together is only 5/6 of that of just the turntable. So it really did not lose that much angular velocity, which is expected because the record is not nearly as heavy as the turntable is, so it doesn't take that much away. So now we're going to do another example, this time comparing the radiuses and how they affect the angular velocities of one person. So let's draw our little person here, and we all know I'm not the great drawer, so we're going to have a little potato person, and its arms are going to be down by its side because then it just leaves the shoulder radius. So, and this person is also going to be spinning about the center of mass, which I'm going to mark with an orange marker. He's going to be rotating clockwise. So now we need to decide shape this person looks most like, so we can have our inertia equation. So we're going to go ahead and go with the solid cylinder. So we're going to draw that out, and then we can go ahead and do our equations. So we're going to draw the cylinder. So the cylinder is going to represent the person because the person's mass is mostly evenly spread out, and the person's radius is going to be his shoulders, which is about even throughout. So now I'm going to mark the center, the axis of rotation for the cylinder. And the cylinder is also going to be rotating clockwise. So now, let's say that the person's mass is going to be 75 kilograms, and then we're going to call his radius 0.2 meters, because that's about normal for a person, a grown person at least. So now, using our equation for inertia, the equation is I equals 1/2 mr squared. And so we're going to take these variables and plug them in, and we are going to get I equals 1.5 kilogram meters squared. So now we can move on. So now we're going to draw another person, and this person is going to have his arms down by his side, also rotating at the same center of axis. It's the same person, same mass, same radius, just drawn a little differently. We all know I'm a bad drawer, my bad. And so this person is going to be holding 2 kilogram weights in each hand, just so we can tell the difference between the first person and the second person, and then we're going to have the third person. So now that we've drawn it, we're going to go ahead and add the arms and the weights onto our cylinder, just for representation. And then we can go ahead and use the same I equation to solve for a new I. So now that we have that drawn, we're going to use the same I equals 1/2 mr squared, but since we already know the original inertia of the person as 1.5 kilogram meters squared, we can use that as the base of our formula, and then we can just add on the inertia of the weights. So it's going to be 2 for the 2 kilograms times 2, because there are 2 of them, times 0.2 squared. Because he's holding a weight in each hand, so he has both radiuses. So we're going to multiply that out, and we should get I as 1.7. Yes, 1.7 kilograms meters squared. And that's not much different from the normal, just because the mass of the person increased by 4 kilograms, which compared to about 75 isn't much at all. So now we're going to go ahead and do our third person with the big radius, but the same mass as the second person. We're going to draw our little person. His arms are going to be out, and he might look a little skinnier, but he's going to have, his radius is going to be 1 meter, because for each arm that's out. So he has a wingspan of about 2 meters. So this guy's holding weights. I just forgot to draw him, I guess. So we're going to use the I equation of 1.5 plus 2 times 2 times 1 squared, which is 1. Because the first 2 is for the 2 weights times 1 squared times the radius, and then times 2 because the weights are 2 kilograms, and that gives us 5.5 kilograms, which is significantly larger than 1.7 kilograms meters squared with his arms down. So that means that radius drastically affects the inertia of each little person. So the smaller the radius, we're going to assume that the faster you're going to spin, and the bigger the radius, the slower your angular velocity. And then we can also say that the inertia of the first person is almost 3 times smaller than the inertia of the second person. So we're going to assume that the angular velocity of the second person will be 3 times larger than that of the third person. So let's go ahead and work that out. So we're going to use L naught equals I naught omega naught, but instead of naught, that's going to stand for out, and Li is going to be angular momentum of the arms in times inertia of the arms in times the angular velocity of the arms in. So if we fill in for our numbers here, we're going to have L out is going to be 5.5 kilograms meters squared times omega out. And then we can go on to our person with their arms in, and so that's going to be L in equals 1.7 kilogram meters squared times omega in. And so because there's no external torque acting on our people, we're going to say that momentum is conserved. So L out is going to equal L in. So then we can set our two equations equal to one another. So 5.5 kilogram meters squared times omega naught equals 1.7 kilogram meters squared times omega in. And so if we divide the left side by 1.7 kilogram meters squared to cancel that side out to get angular velocity in by itself, we're going to get 3.2 kilograms meters squared times omega out equals angular velocity of the person with his arms in. So like we said, the person whose arms are in has about a 3 times as higher angular velocity as the person with his arms out. So that is as we expected. So thanks for watching the video. I hope you learned about the conservation of angular momentum, and I will add our sources at the end.